Welcome to video class 39 and we are continuing our discussion on controllers, and this is the part 2 of that. And let me have a recap of what we just studied in the previous video. That is, this is the basic block diagram of a control system, and the part we are concentrating on is this block, that is the controller. Controller is the main component of a control system because it induces the control. Now, as we know, this controller provides a necessary control according to the input to the controller, and you can see that input comes from the difference of the reference input and the output of the system. Okay, so that results in the error. So in a sense, you can say that the input of the controller is called as the error signal, or we will also call as the actuating signal. So that's why I have labeled this as EA of T, and the output of the controller is usually represented as EC of T. This is still an error, or this is an error, and based on this error this will be producing a control signal, and this control signal will be used for the plant to provide the necessary control so that this output will be always a controlled output. So that is a speciality. Now, based on the relationship between the control signal that this controller provides and the input to this controller, that is the actuating signal, controllers can be classified into a variety of ways. And the basic three divisions are, or three classifications are, as I have mentioned in the previous video, they are the proportional controller, differential controller or the derivative controller, and the third one is the integral controller. And these are the basic control action that you can have, and along with this you can have a combination of that, so that will result in PD controller, PA controller and PID controller. So among this, in the last video we have seen the proportional controller and the differential controller. Now in this video let us see let's start with the integral controller. Okay, now let's start with this integral controller. Integral controller. Now, what is the specialty of this integral controller? Based on this diagram, you can say that the control signal that it provides will be proportional to, it's not proportional to the input, or it's not proportional to the derivative of the input, it is proportional to the integral of the input. So you can write that for an integral controller, the control signal EC of T is proportional to the integral of the actuating signal. So this is again a time domain signal, so the integral of the actuating signal E of T from 0 to T. Okay, you can put the limit, and you can equate with the constant of proportionality, and I'm calling that constant of proportionality as K suffix I into integral 0 to T EA of T dt. Okay, so this is the time domain equation. This one is the time domain equation, right? This is the time domain equation, and let's convert this into frequency domain equation, and that's very simple. You know that is by taking the Laplace transform. So taking the Laplace transform, this becomes EC of S is equal to K suffix I into this is EA of S, right? EA of S by S, right? EA of S by S, right? So this is actually the frequency domain representation, or the frequency domain integral equation, where Ki is called as the integral gain. Ki is called as the integral gain. Okay, now let me see you can have a simple block of an integral controller, and that can be shown as, okay, so this is it. Now this is just a part of a control system. I've just shown you a part of a block diagram with the block Ki by S, or this block represents the integral controller, or integral. This provides the integral control action. Okay. Now let's see. So for a constant input, what happens for a constant input? If this input is constant, or this actuating signal is a constant signal, we know that as you integrate a constant with respect to time, right? K into dt, what happens? This becomes K into t, right? And if you try to draw the block diagram of draw the diagram of this, say this function K into t, that will be a linear graph, right? So you'll be getting a linear graph. So for a constant input, the output linearly increases with time, linearly increases with time, right? Now what happens if the input is 0? If the error signal is 0, then, right, the integral action is 0. For a 0 actuating signal, the control signal remains stationary or without any change. Okay, so the control action will be without any change. Okay, so this type of controller is also called as the reset controller. Reset controller. Okay, this is also called as a reset controller. We have already studied that differential controller can be called as a rate controller. Well, this integral controller is called as a reset controller. So it's because of this. When the input is equal to 0, the control action remains stationary or without any change. And due to this fact, this controller is also called as a reset controller. Okay. Okay. Now let us see the effect of an integral controller. So for that, I am considering a block diagram as shown in the figure. Okay. So here is a block diagram for you, and you are considering a plant or a process whose transfer function is k by s plus a. Okay. Now, as you can see that by looking at this transfer function, you can see that this system or this process is actually a zero order system, right? Because there is no pole over here at the origin. So this is k by s plus a. So this is of the type, it's a type 0 system. Now, this is a block diagram. This is basically that this one is, I mean, you can first of all imagine that you don't have any block like this, so that this is a simple unity feedback system with a transfer function k by forward transfer function as k by s plus a. Now, what we are doing is I'm actually adding a block which is ki by s. And what does this ki by s denotes? Now, that's why I have drawn this. I have found out this frequency domain. This can be written as, this is equal to k into I by s into Ea of s. So this is it. So this is Ea of s multiplied by Ki of s. So this one is the integral block or the integral controller. So I'm actually connecting an integral controller along with this process. Okay. And now we are going to study about the effect of this integral controller. So in order to do that, the first of all what we need to do is, so just imagine that you don't have a controller like this first. So what's going to be the error of that signal? So the error of that signal E of s is actually given by, we have already seen that as 1 plus, okay, gs hs into rs, right? Okay, so this is a relation we have already derived in our previous videos. So that means that this is actually your, and since it's a unity feedback system, h of s is equal to 1. Therefore, this becomes E of s is equal to 1 by 1 plus gs, okay, into 1 into R of S. Okay, now, so based on this R of S, there will be an error signal E of S, and this E of S can be found out as 1 by 1 plus TSHS. So this is your error, and that is without the, so this is actually the error without the controller. You haven't added any controller, without the controller. That is what I meant to say is, so imagine that you don't have anything like this. So if you can find out this error signal by using only this block, then you will get a graph like, you will get an equation like this. So that is 1 plus GS into RS. Okay, now let us see. Now what is your GS over here? So we have considered this K by S plus A as your GS, so that you can substitute that equation 1 plus K by S plus A. Okay, so this is without the controllers. So K by S plus A, or you can write like this as S plus A divided by S plus A plus K. Okay, this the whole into R of S. There is an R of S. Now here assume that you are giving an input, a unit step input, that is unit step, a step input. That means your R of S is equal to 1 by S. So okay, so this will be S plus A into 1 by S, S plus A plus K into 1 by S. Now let us see the steady state error. Now how to find out the steady state error? The steady state error is nothing but limit S tends to 0 S into E of S. We have already studied that. So this will be S into S plus A divided by S plus A plus K into 1 by S. This S and S get cancelled. There is a limit S tends to 0, so that you will be getting the error as A by A plus K, right? So what does this give you? What information? Steady state error is the error as the system reaches the steady state, and what we are expecting for a good system, for a stable system, we are expecting a steady state to be 0 error. The error of the at the steady state has to be minimum, right? So or within the limit of 2% or 5%, and above that we cannot afford. So this is the error. So that means there is an error even at the steady state. So let us see what is going to be its impact when you consider this block. Okay, when you add this Ki by S, let us see the impact on that. Okay, now with the addition of that, what will you be getting? So instead of this GS, so you have, so without the controller, your GS was what? Your GS was K by S plus A, right? Now with the addition of, now the next step is by adding with integral action, or with the addition of integral action, that means I am adding a block on the forward path, that is Ki by S. So you can multiply this, so that your new G of S will be equal to K into Ki divided by, you have an S plus A already, and you have a Ki by S, so this will be S plus A. Now let us see what is your E of S. So as I have done just above, that is, this will be 1 by 1 plus K into Ki divided by S into S plus A, or this becomes S into S plus A divided by, okay, S into S plus A plus K into Ki, K into K suffix Ki, K suffix I. Now how will you find out the steady state error? Now the steady state error is limit S tends to 0 S into, okay, this is into R of S, okay, into R of S, this is into R of S. And what is your R of S? R of s you are giving here also you have given an now what we have to do is we are going to find out the effect of integral controller when you give R of s to be when you give R of t to be unit step. Okay, that is u of t. So that means your R of s is 1 by s. So that's what we have done in without this integral controller. Now I am adding an integral controller and giving the same input so that this becomes s into s plus a. Okay, so you have an s into limit s tends to 0, s into the whole of this. So you have an s over here, s into s plus a divided by s into s plus e plus k into ki, the whole into 1 by s. This is into r of s, right? So instead of this r of s, you can replace that by 1 by s because it's a step input. So this s and s get cancelled. Now when you apply s tends to 0, what happens? What happens? This becomes 0. Okay, this part becomes 0. This becomes k into ki. Well, what about this? S into s plus 0. So this becomes 0. The steady state error becomes 0. So look at the impact of integral action. Now, without the integral action, at the steady state, there will be having an error, and that is equivalent to the parameter of the process. Okay, and the parameters are k and a, so it depends on the value of k and a. So as long as there is a value of k and a, there will be always an error without the integral controller. Now when it comes to an integral action, by putting an integral controller along with this, what happened was we have seen the control system with already a steady state error has been reduced to 0. So this is one of the impact of an integral action. Okay. So what we can conclude is if the plant transfer function is having a steady state error due to a step input, then that can be made to 0 when you add an integral controller along with that plant. Okay. So just now we have seen the impact of the integral action on a type 0 system subjected to a unit step, and it's very clear that the unit step signal for an unit step signal there was an error without the integral controller. By adding an integral controller, it is steady state error. Now let us move on to a case of type 2 system. So for example, consider a type 2 system with the gs equal to k by s into s plus a. So do remember the first case we have considered as k by s plus a, meaning this is a type 0 system, while this one is a type 1 system. So this when you add say when you do this type 2 system, or when you add an integral action, so that means your g of s will be k by s into s plus a. So adding an integral controller means adding another block with ki by ks, by s, right? So the overall transfer function now becomes ki by s into k divided by s into s plus a, right? That is, I mean the forward path, right? So that will be your new GS. Now this is a GS without the integral controller. Now when you add an integral controller, this gets multiplied by this. So you will be having this. Now this is your GSHS, and if you can assume that this is a unity feedback control system, then your h of s is equal to 1. So what must be your GSHS? So GSHS remains this. Now what is the characteristic equation? The characteristic equation is 1 plus GSHS equal to 0. Or you can say that 1 plus k into ki by s square into s plus a is equal to 0. Or in another sense, you can write s square into s plus a plus k into ki is equal to 0, right? Okay. Or this can be written as s cube plus a into s square plus k into ki is equal to 0. Now, the first of all, the one of the thing is that you can notice you can have a missing term between a square and a constant term, right? A missing term of s raised to 1. So this itself proves that there must be at least one right half false. Okay, one right half false. So you can just prove it by applying Rutherford's criterion to this. You know how to draw this. So s cube and s square draw. I mean, the coefficient one will be 1. What about s raised to 1? That is 0, right? Now the second row will be filled by the a. Then this one will be k into ki. Now what will be your s? S will be found out by a into 0 divided by minus k into. So this will be minus k into ki by a, right? Minus k into ki by a. And you don't have to do anything rest. You can see that no, when you write it in the note, you can complete this. I'm just showing you that by when you apply the same thing when in integral action to a step 2 system, when we have analyzed the characteristic equation, we can see that there is there is a one change, right? This is a is a positive quantity, so now these two are positive. Now it becomes a negative sign. So that means there is a change in the sign, meaning that there must be at least one right half false. That's what Rutherford's criterion says. So when you add an integral action to this type 1 system, what we found out that is because of the effect of this integral, you have from the characteristic equation applying Rutherford's criterion, we have seen that there is at least one right half false in the S plane. That means the integral action will make a type 1 system to an unstable system. But for a type 0 system, it is good. For a type 0 system, it will make the steady state error to 0 for unit input, step input, while we have seen that when you add the same thing to a type 1 system, that will make the system unstable. Okay, so that's the impact on the impact of the. Now you can summarize this. Number one, the summary of this, that is for a constant signal, for a constant actuating signal, the control signal or the controller provides a signal which increases, control signal increases linearly. Okay, as I have shown you, when you give a unit step constant input, since it integrates, the integration leads to a linear increase. Now second one is if the actuating signal is 0, then the control signal remains constant or stationary, and because of this reason, this is also called as a reset controller. Now the third point is for a type 0 system, subjected to unit step signal, the integral controller makes the steady state error to 0. While what is the fourth condition? While for a type 1 system, the same integral controller can make the system unstable. So these are the four important points regarding a proportional integral. Regarding the integral controller. Okay. So for what we have seen is regarding controllers. Individual, we have already seen that controllers are of three different types. So that is they are proportional controller, differential controller, and integral controller. And so far we have seen all these things. Okay. Now so we have seen the advantages and the drawbacks of each controllers individually. Okay. Now, in a practical purpose, usually what we can see is, especially in industrial purpose, we'll be using a combination of all these controllers, okay, so as to get the benefits of or the advantages of all controllers together. So, based on that, you can have three different combinations. That is a proportional derivative controller, proportional integral controller, and proportional integral derivative controller. So these are the common combinations that can be used, that is seen or that's used in industrial purpose. Okay, so now let's start with the combinations. Okay, so we have already seen proportional, differential, and integral. Now we are going to see some of the combinations of this. So to start with, we are going to start with the proportional plus derivative controller, or in short we call it as the PD controller. So the block diagram of that can be shown as follows. A simple, this is just a part of a block diagram, and the block can be the block which relates to proportional plus derivative controller can be represented by Kc plus Kd into S, and it is then fed to a plant which is to be controlled. So this is just a part of a block diagram of a system. So here you will be having a system, it's connected to the system, and this is the controller part. And as you know that this is the actuating signal or the error signal, and based on this error signal, this controller will provide a control signal which is able to control the process which is connected over here. Okay, so this is simply a block, a part of the block diagram. Now I will explain how this block comes, or how this Kc plus Kds came. So we know that this in a proportional plus derivative control, the definition of this type of controller is you have the actuating signal and the control signal. Okay, now what it refers to is the see what it refers to is EA of this is EA of S or EA of T, EA of T, or the actuating signal, EC of T, that is the control signal, is proportional to the actuating signal EA of T, or it can also be proportional to the derivative of EA of T. So that is, this particular controller is a controller which provides a control signal according to proportional to the error signal, as well as it is proportional to the derivative of that error signal. Okay, so so what is this Kc and Kd? I will just explain. Now you know what is Kc and Kd, we have already seen. Kc is the proportional gain, Kd is the derivative gain. Okay, now let's see, or it is also called the rate gain. So that means from the definition of a proportional plus derivative, you can write the equation for this time domain equation. That is, the control signal is nothing but, it is, I have told you, it is proportional, it is the sum of the proportion, it is proportional to the actuating signal as the derivative signal. So when you equate, we need to do put the proportionality constant, which we have already defined. This is the proportionality constant for a proportional controller, so that means this is equal to Kc into EA of T plus Kd into the derivative of EA of T. Okay, so this is the we got from the basic definition of a proportional plus derivative controller. Now what if I transfer this time domain function to S domain? So when you apply the Laplace transform, this EC of T becomes EC of S is equal to Kc into EA of S plus Kd into S into EA of S. So all these things you know. Here you will be assuming the system to be a relaxed system, or the initial condition is 0. Now you can take EA of S outside, so that this becomes Kc plus Kd into S into EA of S is equal to EC of S. So from this you got this block diagram. That is, if you have the actuating signal, you will be getting the control signal by placing a block of Kc plus Kd S in between this EA of S and EC of S. Okay, so this is how this block diagram came. Now this from this equation, now from 1 you can have a manipulation by taking this Kc outside. So when you take Kc outside, this becomes EA of S into Kc into 1 plus Kd by Kc into S, or this Kd by Kc is defined as a TD, or it is designated as a capital TD, or this is called as a derivative time or the rate time. Okay, so this will be having a dimension of time. Now, so that you can rewrite that equation as EC of t is equal to EA of S into Kc into the whole into 1 plus TdS. Now, to give you a feel of this, feel of the action of this proportional derivative controller, I'm going to start with an example. Suppose that your actuating signal is a ramp signal. That means, what I mean to say is it's a unit ramp. Unit ramp means your k into t, where k is equal to 1 or the slope is equal to 1. Okay, so you have such a signal at the input side, right? At the input side, and as per the definition, you can write the equation for this EC of t or the control signal, and that is being given as Kc into t into u of t. This is the proportional part, and this is the derivative part, Kd into the derivative of that t into u of t. Now, you don't have to consider this u of t again, you just need to differentiate that. So this is EC of t is equal to Kc into t into u of t. U of t is 1 plus Kd into the derivative of t. Okay, so the derivative of t with respect to time is 1. So this is equal to Kd. So look at this. So this expression becomes EC of t is equal to Kc into t into u of t plus Kd. So this sounds similar to y is equal to mx plus c. Mx plus c, where x denotes the time t. So I'm going to draw this. X denotes time t, while Kd, so this is a straight line which passes through the y-intercept. Okay, there is a y-intercept, or which is not a line which passes through the origin. So keeping all these things in mind, you can see that this will not be a unity slope. Okay, we started with a unity slope signal, but what happened is we got a different ramp input with a different slope, and the slope is equal to Kc, right? So the slope is proportional to what? This slope is determined by Kc, right? Or what is Kc? Kc is the proportional gain, while there is always at the zero this there is always a at t is equal to 0, there is an offset of Kd, which is actually the parameter of the derivative controller. So look at this. So because of this ramp signal or the error signal has been shifted by equal to Kd, which is the derivative controller gain, and not only that, its slope has been changed from unity to Kc, which is nothing but it is the proportion. Now let us see to study the effect of this PD controller by considering an example. So here is a block diagram for you. So this one actually represents a plant, right? This one represents a plant. This one represents the plant, or the process which is to be controlled, or this k by s into s plus a is the transfer function of that particular process, where k is it can be the forward path gain, s into s plus a. And in addition to this, I have attached a controller called as a PD controller. Now we know that the PD controller block is Kc plus Kd into s, and it is connected in series to this, so that your g of s becomes the combination of the product of this transfer function. This is the transfer function of a PD controller. This is the transfer function of the plant. So since it is cascade together, this is G1 into G2. So you can combine these two into a single block. So that will result into a G, right? So this is actually a canonical form, right? The canonical form and a negative feedback system, so that you can use this expression Gs by 1 plus GSHS, where Hs is equal to 1, right? So using that, and you may do that by yourself, so that you will be getting a C of s by R of s as k into Kc plus Kd into s divided by s square plus a plus k into Kd into s plus k into Kc. So do remember, you have three constants. One is k, which is related to the plant, while Kc and Kd are related to the controllers. Kc is the proportional controller gain, Kd is the derivative controller gain. Now this is actually the transfer function. Now suppose for the meantime you are considering a case where you don't have the derivative control. Suppose you have only the proportional controller. So if there is no derivative control, this is basically a basically a proportional controller. Okay, even if it is 1, even if this block is 1, that is also a proportional controller, because that is output is proportional to the input, right? So even if this is equal to 1, that is a proportional controller. So basically all these controllers are proportional controller, but along with that you are attaching what? Derivative controller. So imagine that. So we are going to study the impact of connecting a derivative controller along with the proportional controller. So what happens is, if there would have been no controller, that is without a derivative controller, what's the meaning of that? Your KD becomes equal to 0. KD becomes equal to 0 means this part becomes 0, this part becomes 0. So resulting in what? K into Kc, right? This is 0 divided by S square into A into S plus K into Kc. So this is actually C of S by R of S, or it is equivalent to 1 plus GSHS. Now if you can equate this denominator to 0, you will get the characteristic equation of the system with only what? With only this thing, no? This is K into, okay, with only proportional control, right? With only proportional control. Okay, so and that means, as I told you, that it is you can assume this KD to be 0 and KC to be equal to 1. Okay, so that means there is no specific proportional controller. It is equal to 1. That means the whole signal that comes over here is directly fed to, it is as if it is directly fed to this plant. That is, it is without any controller. So you can say that it is without any sort of control. So meaning that this KD and KD is equal to 0 while KC is equal to 1, right? So that your equation becomes S square into S square plus AS plus K is equal to 0, or this is equivalent to S square plus 2 zeta omega ns plus omega n square, which is the characteristic equation of a second order system. Now in comparison to this, you can see that omega n square is equal to K, or omega n is equal to root K, right? Now this zeta omega n is equal to A, small letter a, right? So from this you will be getting zeta to be equal to A by 2 omega n, right? So this is actually the case with the zeta without a proportional derivative controller. So this is without PD controller. Now what happens when you connect this Kc plus KD? So assume that, now don't put Kc is equal to 0, because it is as if you put Kc is equal to 1, it is as if without any sort of proportional controller. That's what we mean. Now Kd is 0 because there is no derivative controller. Now once when you connect this Kc plus Kd, you can see that the characteristic equation is this one: S square plus A plus K into Kd into S plus K into Kc. So now if you have a comparison again to this general characteristic equation, you can see that omega n is equal to, look at this, omega n is equal to root of K into Kc, right? And we also know that 2 zeta omega n is A plus K into Kd. From this you will be able to get zeta value to be A plus K Kd divided by 2 into root of K into Kc. So you can see that, in comparison to, so call this as, 1 and this as 2. So 1 and 2 both are the equation for zeta. So the 1 is actually the equation for zeta without PD control, while 2 is an equation with PD control. Now when you connect this PD, there is always when you look at this equation, there is only one K, right? That is, K is actually a parameter which depends on the plant or the process. So once the process is designed, you cannot change the value of K. So that zeta can be any value from 0 to 1. So as we have seen that in our frequency domain specification, say as long as zeta lies in between, say some 0.723 or something like that, there will be always a maximum overshoot, and the maximum overshoot will not be there if zeta is greater than. So it's always greater than this value. Okay, so as zeta approaches to 1, this maximum overshoot or the transient response becomes better and better. Okay, now once you have set this, designed this process, it's not possible to change the value of K. Now When you introduce when you try to connect a PD controller, there is now, looking at this equation, there is a provision to suitably selecting your KD and KC. That is a proportional gain as well as a derivative gain. By suitably selecting this, you can improve the value of theta. Now, what is the consequence of improving the theta? Now, as you improve theta, maximum overshoot gets reduced, right? And not only that, settling time also gets reduced. So, in a sense, you can say that, the transient response will get improved. So, I'll be explaining when we summarize this. To summarize the various aspects of this PD, by properly selecting this KD and KC, theta can be improved, right? Now, on the consequence of that, it reduces the maximum overshoot and reduces the settling time. Now, we have already seen the second order system like this. So, the settling time, it becomes faster, or the settling time gets reduced, means it gets faster. Okay. Now, the overall improvement is there in the transient response, and overall, because of the derivative control, yes, as we have seen in the proportional, when we studied the individually proportional and derivative, the drawback of proportional is it is sluggish or lazy, while the derivative means it enhances, or it makes the response faster. So, in conjunction with the derivative, so you can see that so when you implement this, when you add this derivative along with the proportional, the whole system is getting that advantage of the derivative controller, which makes the response faster, and finally it increases the bandwidth. Okay, now let's move on to the proportional integral controller, or in short you will call it as a PI controller. So the basic block, a part of a block of which is a block of a control system which is connected by a proportional integral controller is given as shown. The additional block that we need to add is Kc plus Ki by S. This is actually Ki by S. So inside the block you can see that this is Kc plus K suffix I by S, where Kc is the proportional gain we have already seen, while Ki is the integral gain. Now let us see how this block comes. So I'll be explaining right now. So this can be explained as, say, we know that this is your actuating signal EA of t. Okay, the signal that comes over here is actually EC of t, which is the control signal. So what is this control signal? EC of t is actually, it is the proportional to Kc into EA of t plus Ki, Ki integral, okay, it is Ki into integral, where this is a constant into, it is proportional to the integral of what? Integral of the actuating signal. So how will you define the proportional integral controller? So proportional integral controller is a controller which gives a control signal which is proportional to the actuating signal as well as proportional to the integral of the actuating signal. So combining this, using that definition, you can write this equation. So when you write the time frequency domain equation for this becomes Kc into EA of S plus Ki, okay, K suffix I, right, into EA of S by S, right? So in some textbook you can see that it is integral from 0 to t. Okay, so this will be K by S into EA by S, or so you can write this EA of S. You can take EA of S as constant, common, so that this becomes Kc into Ki by S. So this forms the block diagram. Okay, now you can have again a manipulation like this, EA of S into Kc. You can take the Kc outside, so that this becomes 1 plus Ki by Kc into 1 by S. Okay, so that means this becomes equal to EA of S into Kc into 1 plus, it is, do remember there is a slight change, it is 1 by TIS, where Ti is defined as Kc by Ki. Okay, earlier we have defined a Td, which is actually Kd by Kc. This is Kc by Ki, or this is called as a integral time or reset time. This is called as a reset time or integral time. Okay, right? Okay, so to give you a feel of how this proportional integral controller behaves, you're assuming EA to be a step input. Okay, assume that EA of t is a unit step signal, so let it be U of t. Okay, so once this is U of t as per this equation, so let us try to find out the control equation, that is EC of t will be Kc into U of t, right, plus Ki into K suffix I into integral, say some integral U of t, okay, U of t dt, right, that is you are integrating 1 over dt over, okay, so that this becomes Kc into U of t plus, right, Ki into t, right, so this is Ki into t. Now this is again, as I have explained earlier, this is again equivalent to y is equal to mx, right, sorry, so this is actually equal to, this is mx plus c, right, okay, so this is Kc into U of t, or so this is equivalent to y is equal to mx plus c. Now instead of y you have your Ec of t, that is a control signal, this is your t, so that you can see that it passes through, it's not passing through an origin. So this was the signal that we supplied, this was the input, right, this was actually your Ea of t, but what you're getting is actually equal to Kc plus an addition, an offset. You can see an offset starts at Kc, that is at t is equal to 0 you will be having a value Kc, and it is having a straight line which passes through this Kc. So this is how it goes. So as you give as the actuating signal is a step input, what happens is the controller output will be a ramp signal which is having an offset of Kc equivalent to the proportional gain, and with the slope, what is the slope then? The slope is determined by this Ki, that is the integral controller gain or the reset gain. Okay, so this is how the graph looks like, right? Okay, now let's try to study the effect of PI controller. So for that you are consider a block diagram as shown. Okay, so the block diagram, as you can see that this is a unity feedback uh, gain, and suppose if you are hiding these two, this block as well as this summer, it is simply a direct system with the g of s with a process. So this is actually the transfer function of the process. This is to be controlled, and you have a unity feedback. Along with this you are attaching a controller, and that is a PA controller. Now this is a proportional integral controller, therefore this can be represented by Kc, which is the proportional current gain, while Ki, which is the integral gain, Ki by S, and this is a disturbance. Okay, so first of all what you need to do is, so there are two inputs, so you can have a, so we are assuming that the system that we consider is a linear system, that means it follows the superposition principle. So first of all, say let me take a case where there is no, that is an ideal case, there is no disturbance, that is ds is 0, as if you don't have this. So you can combine these two blocks, right, since there is no, if there is no ds, then there is no point in placing this sum over here. So that means this two comes in cascade. You can combine these two blocks as a two products. So this is, if suppose this is g1, this is g2, this can be written as g1 g2 under this d of s. Okay, so making that and considering your h of s to 0 using the canonical equation, you can derive the transfer function without disturbance. Okay, so what you are doing is you are actually finding out the transfer function without disturbance. Okay, so this is the ideal case. So there is no disturbance. So your transfer function becomes, so you can prove it. So you may do it by yourself and you will arrive at this expression k into kcs plus k suffix I divided by s cube plus a square plus k into kc into s plus k into ki. Okay. Now, as you can see that when we have assumed that d of s is equal to 0, when d of s is 0, that means you can multiply this, you can consider this as g1 and this as g2, right? So, what will be the overall g of s? G of s, the overall g of s will be g1 of s into g2 of s, or it is equal to kc plus ki by s the whole into k divided by s into s plus a, or you can after different simplifications, okay, now you can write like this. This will be k into kc plus k suffix I divided by s square into s plus a. Okay, so this is your effective g of s of this. Now what must be your g of s h of s? So g of s h of s will be the same thing because h of s is equal to 1, right? So that means when you, so this is actually the open loop transfer function of this system when d of s is equal to 0. So comparing to the open loop transfer function, we can see that since there is an s square, this is a type 2 system. Okay, type 2 system, right? Meaning there are two poles residing at the origin. Okay, now we have already studied about the steady state error. The steady state error due to step and ramp input for a type 2 system is equal to 0. Okay, so we have already studied. If you have any doubts, you may refer the previous videos where we studied about static error coefficient. Okay, now so for these inputs the steady state error is 0. So that means there exists only one acceleration error coefficient, which is given by k into limit s tends to 0 s square into gs hs, right? gs hs, or you can just write down s square instead of gs hs. You can write this as k into kc plus k suffix I divided by s square into s plus a, right? This s square and s square get cancelled. So putting s is equal to 0, you can see that you will be getting this as k. Okay, then you have a you have a kc. Okay, so this will be k by square. Okay, so there is a mistake here. It is when you do take the LCM, there you will be having a kc into s. So you may just do the correction kcs plus ki. So here also you will be having a kcs. So putting s is equal to 0, what happens is this will become k into k suffix I divided by a. So this is actually the acceleration error coefficient, and for a parabolic input, you have seen. So you may just refer those videos if you have doubts. The steady state error is 1 by the acceleration error coefficient, or it will be a divided by the k, which is actually the system gain, into I ki. Ki refers to the integral gain or reset gain. Okay, so we can see that the error can be minimized, the steady state. So this is actually the steady state error. Okay, the steady state error can be minimized by properly choosing this ki. See, once designed the system, k is always it's constant, you cannot change. but you can design an integration. I mean, okay, the integral. You can design the integral gain. Okay, so by suitably selecting your ki, you can improve your ess. So as per this thing, if you can increase your ki, you can reduce the steady state error. So in a sense, you can see that by the introduction of an integral controller, the steady state response gets improved. In the derivative, we have seen that the transient response has been improved. That is what I meant to say is, the graph, this is actually the graph of a second order response for a step input. Okay, I'm just giving you an example. So this region is actually the transient response, and this region is the steady state. So the derivative will be improving by the introduction of derivative controller along with proportional. What happens is it improves the transient response, while by the introduction of an integral controller, that improves the steady state response. Okay, so that is the advantage of an integral controller. Okay, now let us see to study the effect of disturbance. Now here in this figure, we have just assumed that d of s to be 0. Okay, now we are going to study the impact of d of s. Okay, and for that, what we do is we will make r of s to 0 and we'll consider only the effect of d of s, and that is next. Okay, now when you make this r of s to 0 to study the effect due to d of s. Okay, that is due to disturbance. So you are considering this d of s, right, while making r of s to 0. So you're putting r of s to 0. What will be happening to this when you make r of s to 0? When you make r of s to 0, look, this particular thing becomes the feedback, right? Becomes a part of the feedback, and this is only the forward path gain. So that means, your C of s to R of s, is going to be equal to, okay, C of s to R of s is going to be equal to K into S divided by S cube plus A square plus KCS plus K suffix I. So you may just do it by yourself. That is considering your G of s to be K by S into S plus A. Your H of s to it now, H of s is no longer equal to 1 because you are considering the disturbance. So this becomes a part of the feedback. So your H of s becomes Kc plus Ki by S. Using that, when you do the when you use the canonical equation, you will be arriving at this expression. So this is the transfer function when you consider the disturbance. Now let us see what is this actuating signal from this. So look at this. So actually, when you look at this, the actuating signal. So now this has got no effect. So this becomes a feedback. So the input that comes at the controller will be C of s. So what must be the control signal? The control signal. So the actuating signal that comes over here will be minus of Cs, right? So EA of S is actually equal to minus C of S, right? Or you can say that is equal to minus C of S, right? Right? So what will be your sorry, this is K E A of S divided by D of S, right? This is not R of S, this is D of S, right? So what will be your C of S? This is C of S will be Ks into D of S divided by S cube plus A square plus KCS plus Ki, right? This is E of S. So putting a negative sign. Okay, so from this C of S will be Ks into Ts. Okay, now so do remember that we are considering your R of S to 0, then the transfer function will be C of S by D of S. Okay, So you may just do that correction. It is not R of S, it is D of S. So from this you got this as like this. Now the steady state error in the actuating signal due to a step disturbance is 0, and due to a ramp disturbance input is let's see what is the steady state error EAA of this disturbance. So how will you calculate that? The disturbance error, it will be limit S tends to, assuming your D of S to be an unit step. So unit step means D of S is going to be 1 by S. Now using that, you can write this limit S tends to infinity, okay, minus S tends to 0, K into S into D of S divided by, okay, S cube plus A square plus KCS plus KI. Okay, so this is it, S divided by, and this divided the, what is D of S then? The D of S will be equal to 1 by S, right? Now you will be getting this as, you can see that when you put A is equal to 0, you can put that K by Ki. So this is minus K by Ki, right? So here also the steady state, as we have seen here, the steady state error can be improved by the value of Ki. So due to the disturbance also, there can be some steady state, that can be, the steady state error can be minimized by using suitable values of Ki. So for both the cases, that is for the when we considered only the input also as well as the disturbance also, for both the cases you have seen that the integral controller gain or the integral gain has a great impact on the steady state. So thereby proving that it improves the overall steady state response. Okay, now let us see what will be the characteristic equation of this system. Okay, what will be the characteristic equation of this system? The PI controller. So the characteristic equation, when you write down what is characteristic equation? Characteristic equation is 1 plus GS HS equal to 0. So for this case, or you can see that this is S cube plus, so here it will be S cube plus A square plus KCS plus KI is equal to 0. Okay, now so it can be seen that so this is actually your characteristic equation. Now if Ki it becomes more large, right, in this characteristic equation from root locus information we know that as you increase K, it can go to instability state. And another point is, if I am using only the integral controller, okay, now what will happen if I am using only integral controller? I am not considering your Kc, right? Okay, so I am not considering the purely integral controller. That means I am making this Kc to 0. The characteristic equation becomes S cube plus A square plus Ki. Okay, so that means there is a missing in one of the powers. So the characteristic equation becomes equal to 0. And what does this mean? This means that there will be always one roots will be, or roots on the this shows that there is a presence of roots on the right half plane, meaning this is always an unstable system. Or while controlling a system, this proves that you cannot use the integral controller alone, right? So integral controller has to be used along with the proportional controller to derive its advantage. Otherwise, if you are using only purely integral controller, then that integral controller can make the system unstable. Okay, hope you understood this. Okay, now let us summarize the features of a proportional integral controller. Number one is the steady state error, as we have seen, can be minimized, can be minimized by increasing ki, which is the integral gain or the reset gain. Okay, so we have seen that for both the cases, that is for the effect of input as well as for the disturbance, we have seen that it depends on the value of ki. Okay, now the consequence of this is, as you increase ki, there is another problem which we have already learned from root log, is that the system can turn to instability as you increase the value of k. So there is always a risk of system to go to unstable state for a very high values of ki. Now another thing is that the third one is, we have seen from the disturbance, from the effect of disturbance input, is it is also reduced. So this is the consequence of this. Steady state error can be minimized, means the effect of disturbance in a circuit gets reduced. The effect of disturbance gets reduced due to the fact that it reduces the steady state error. So that is another feature of this integral or the proportional integral controller. Now another point we have noted is, see, on the introduction of this ki, the characteristic equation becomes what? The characteristic equation becomes a third order equation. Actually, we started with the system which is a second order system. This is of the form s square plus as. So this is actually a second order system, but by the introduction of this integral, the second order system gets converted to a third order system. Okay, so these are the features of this PI controller. Now finally coming to the last combination, which is proportional integral derivative controller, or in short it is called as a PID controller. Now the basic block diagram will be, or the part of a block of a system containing a PID controller can be drawn as, say this is negative, this is R of S. So this is actually Kc plus Ki by S plus Kd into S. Okay, now how you got this? This is very simple. This is your control signal, this is your actuating signal. The relationship between actuating signal and control signal will be EC of t will be equal to, okay, Kc into Ea of t, right, plus Ki into integral Ea of t, right, dt, plus Kd into derivative of Ea of t, right. So this is the equation. Okay, this equation is we got from the basic definition of a PID controller. This offers not only the output is proportional to the input, it is also proportional to the integral of the input as well as the derivative of the input. Now from this, when you convert it into frequency domain, you will get this as AC into Ea of S plus Ki by S into Ea of S, right, plus Kd into S into Ea of S, right. So this is actually Ea of S into Kc plus Ki by S plus Kd into S, right. So you will be getting an equation like this. So that is how a block you will be getting a block like this. Now what you need to, in order to complete this block diagram, you fix a plant, and the plant will be having a transfer function. So as we have seen in the previous example, it can be K by S into S plus A or whatever it is. So anyway, the advantage of this PID controller is it extracts the advantages of a proportional, integral as well as a derivative. Even if there are the drawbacks of each, that can also be minimized by putting some limits on this. For example, one of the drawback which we have seen in the integral is, as you increase more Ki, that system can lead to instability. So if you can put a limit to that increasing value of Ki,
you can restrict the system to go to an unstable state. So thereby you can do some restrictions. Giving all such restrictions, you can derive the advantages of each controller in a PID controller, so that this becomes a more effective controller as far as the performance is concerned. So these are the three important. I'm going to summarize this. I'm not going to into the details of the mathematical analysis. Just the so this type of controller, since this is a combination of this will be having a PD mod and a PI mod, right? That is a proportional derivative mod and proportional integral mod. And the PD mod, that is the first significance. The PD mod of control improves what? We have already seen that it improves the transient response. That means, what's the meaning of that? It reduces the maximum overshoot, increases the settling time, right? So and it is again a nature of a derivative controller. Big on consequence of this is the system becomes faster. Okay, so any system, if it becomes faster, it is due to the result of this derivative controller, because derivative always makes the system faster, thereby reducing the settling time. Now, what about the PI mod? What the PI mod is, it reduces the steady state error, or effectively it improves the steady state response. So we know that for any system, the output response can be have to, you can have you can divide that into two: transient response and steady state response. Now, by the use of derivative control, that improves the transient response, and by the use of PI mod, that improves the steady state response. So overall, that whole response is going to be improved due to the usage of PID controller. Okay, hope you have understood all these things.